Hello everybody, I am Greta Vallero, a PhD student from Politecnico di Torino. I'm going to present a work co-authored by Professor Michela and myself. This work focuses on the modeling of an unmanned aerial vehicle equipped with a base station and powered by an onboard battery and an onboard PV panel. In 5G and beyond 5G systems, mounting a base station on WAVs has been proposed as a promising solution to dynamically support the radio access networks in case of terrestrial network failures due to network physical unavailability or overloads, like natural disasters and overcrowded events such as concerts. WAV base stations adapt their aerial position where needed, flying over users who cannot access the radio access network through the ground base stations. These users are connected to the WAV base stations through access links and reach the core network by backhaul links established between the WAV base station and an access point. While the WAV base station represents promising support for the radio access network service, the challenge related to the scarce onboard energy availability needs to be addressed. This is because the used energy is only provided to WAV base stations by onboard batteries. This is an issue which actually characterizes WAVs in general, but when they are used as communication infrastructure, the situation worsens. Indeed, besides the energy needed for the flight of the WAV, also the communication unit has to be powered to provide the service. This results in a higher energy consumption and reduction of the WAV base station lifetime. To cope with this, solar-powered WAV base stations have been proposed, which does not add significant mass to the device. While the solution is promising, several issues need to be tackled, such as the solar panel dimensioning and the understanding of the effect of the intermittent energy production on the communication service. In order to address this issue in this work, we consider FM2cell base station equipped with multiple antennas using the multi-user, multiple inputs, multiple outputs. We assume that the WAV base station is equipped with an energy battery and a PV panel. The PV panel is used to supply the communication unit of the drone, while the battery is used to make the drone fly. In this work, we focus on the PV panel, which produces energy for data transmission. Our objective is to study the dimensioning of the PV panel system, and we investigate the interplay between the traffic demand and the energy generation. The WAV base station is modeled as a queuing system with M servers, where each server represents a single MIMO antenna. The data flow is discretized in data packets, and the waiting line in which they wait to be transmitted is assumed to be infinite. We also use a discretized representation of the energy flows as energy packets. Each energy packet represents the amount of energy needed for the transmission of each data packet. This means that to transmit a data packet, a server needs an energy packet. So, as soon as the server ends the transmission of a data packet, it switches to sleep mode until an energy packet arrives. When this occurs, if there is at least a data packet in the data packet waiting line and an available server, which means a sleeping server, that server is activated and a new transmission starts. In case an energy packet reaches the system while all the servers are busy sending data packets, that energy packet is considered lost and cannot be used for the transmission of a data packet. Actually, that lost energy packet is not wasted, but moved and stored in the energy battery and employed to supply the WAV base station mobility. In case when an energy packet reaches the system, if there are no data packets to be transmitted, that energy packet is lost as well. Data packets and energy packets arrive at the system according to Poisson processes with rate lambda and beta. The data packet transmission time has an exponential distribution with rate mu. We start by analyzing the base station equipped with a single MIMO. And this is modeled as a single server queuing system. As mentioned before, when the server completes a service, it switches to sleep mode until an energy packet arrives. When an energy packet arrives, if there is a data packet in the data queue, a new transmission starts. This means that before its processing, a data packet waits for the arrival of an energy packet, and during this time, the server is on a vacation, waiting for the next energy packet arrival. This is modeled as a sleeping box before being processed. The time spent in the sleeping box is exponentially distributed with parameter beta, and we call it sleeping time. Once this time expires, which means when an energy packet arrives, the server is reactivated and the actual transmission starts and lasts for the transmission time exponentially distributed with rate mu. The service time is defined as the time a data packet spends in the orange rectangle. This means that the system can be modeled as an MG1 queue where the probability density function of the service time G is the sum of two independent exponential random variables. The mean value of G is computed as indicated here. Since the system is stable if lambda times the mean value of the service time distribution is lower than 1, it is possible to derive the values of lambda which stabilize the system. We now derive the probability that an energy packet is lost, which is the probability that an energy packet is lost because when it arrives, no data packets are present in the system. If this is the case, the server remains in sleep mode and no transmission starts. It is given by the probability to find the queuing system empty, which is reported in this purple rectangle. Then there is a second contribution, which is given by the probability that the energy packet is discarded, since when it reaches the system, the server is active and transmitting a data packet. This is the probability that the queue is not empty, derived as in the red box. We now discuss the base station equipped with multiple MIMO antennas using MultiUser MIMO. This is modeled as a multiple server system, and each server represents a single MIMO antenna. The system can be modeled as a bidimensional continuous time Markov chain in which the state S is given by D, which is the number of data packets in the system, both waiting and being transmitted, and P, which is the number of servers that are transmitting a data packet, that is the number of transmitting MIMO antennas. Arrivals occur with rate lambda and increase by 1 the number of data packets in the system D. A departure of a data packet occurs with rate p times mu, where mu is the service rate and p is the number of servers that are transmitting a data packet. Finally, a transmission starts if there are available servers, so if p is lower than m, some data packets that are waiting, and an energy packet arrives with rate beta. To study the ergodicity of the system, let's now focus on the maximum service rate that can be reached. This is reached when the load is high and there are always data packets to transmit. In this case, as soon as an energy packet arrives, a transmission can start if some server is available. The probability to lose an energy packet in these conditions is the probability that an energy packet arrives and finds all the M servers already busy. Since there is not an energy packets line, this is given by the probability given by the Erlang formula. So, the maximum service rate of the data packet queue with multiple servers can be computed as reported, and from this, the values of lambda which stabilize the system can be derived. From the solution of the Markov chain, under the ergodicity condition, it is possible to derive the probability that an energy packet is lost, which is the probability that an energy packet is lost because it finds no data packet that needs to be processed, and the probability that an energy packet is lost because when it arrives, all the servers are already busy processing data packets, computed as indicated where pi of d and p is the steady-state probability to have d data packets and p servers that are processing data packets. Now, the models previously discussed are verified by simulations. We simulate our scenario with different numbers of servers from 1 to 4 with beta, mu, and lambda as reported here. We measure the energy packet loss probability, which is the probability to lose an energy packet. This probability is shown versus lambda, and the cases with different numbers of servers are reported in different colors. Vertical lines show the ergodicity condition on lambda. First, we observe the two different regions which correspond to the queue being stable or not, and that differ for the behavior of the loss probability. For low values of lambda, the queue is stable. Interestingly, when the system is stable, the energy packet loss probability assumes the same values independently on the number of servers. Let us now focus on the ergodicity condition. Why increasing the number of servers from 1 to 2 has an important beneficial effect on the maximum service rate, any additional server produces only marginal improvements which tend to vanish. Indeed, by increasing the number of servers, the maximum service rate converges to the energy packet arrival rate beta. In order to further increase the system service capacity, a more powerful energy production system is needed. Now, using real data, we consider the hourly variation of the energy packets and data packets rates to shape the hourly fluctuation of the energy production and of the traffic demand. We focus on daylight time from 8 a.m. to 5 p.m. and we assume that the WAF base station is located at 120 meters from the ground. On the x-axis of these plots, the PV panel capacity varies from 0.8 watt to 83 watt, which guarantees the feasibility of the system in terms of carried payload. The green and red bars in these plots indicate the values of the PV panel capacity which make the system stable and unstable during each hour, reported on the y-axis. When the system is unstable, the energy is not enough to serve all traffic demand. Results are here given for two different values of traffic demand in summer and winter. These figures show that low traffic demand can always be satisfied even in winter with limited energy production, while high traffic demand is satisfied only in summer when the energy production is high and large PV panels are considered. Larger PV panel capacities are needed to serve the traffic demand during low energy production hours from 8 a.m. to 10 a.m. and from 2 p.m. to 4 p.m. Then during the peak energy production period from 11 a.m. to 1 p.m. So, to conclude, in this work we model a multiple-user MIMO WAF base station powered by a PV panel. Our results reveal that this solution is effective to cope with the scarceness of onboard available energy of WAF base stations. Nevertheless, the PV panel has to be properly sized in order to operate in stability conditions, evaluating the period of the day and of the year. As future work, we will investigate the effects of the power exchange of the PV panel and the onboard battery used for the WAF base station flight supply. So this concludes this presentation. Thank you